Hello everyone. Today we are going to see haloalkanes and haloarenes, or you can call it as alkyl halides and aryl halides. We are going to cover this chapter as two parts, which chapter includes preparation and properties of haloalkanes. First of all, we are going to understand the nature of CX bond, followed by how it is behaving, how it can be produced, and after that we are going to see what are haloarenes and the naming of them, SN1 and SN2 reaction mechanisms, which is nucleophilic substitution reactions, and preparation and properties of haloarenes compound. So let's get started from the basics. We know halo means halogens, F, Cl, Br and I. Mostly these four halogens we are talking about. Okay, so while naming those things, we have to use fluoro, chloro, bromo and iodo. Talking about the nature of CX bond, when it is forming a bond with alkyl group, CX bond, in that case, since this is more electronegative, halogens are more electronegative, it becomes polarized. It is pulling the electron cloud of carbon towards the halogens, which makes it polar compound, and the bond length increases from CF to CI, which means CF is having shorter bond length, then comes CCl, then comes CBr, and then finally CI. Why is it so? You can see iodine is bigger in size and less electronegative when we are compared to the fluorides. Then, talking about the physical properties of haloalkanes, it decreases with increase in branching. What decreases? Boiling point. We already discussed about this in previous organic chapters as well. The boiling point of isomeric haloalkanes decreases with increase in branching. Which means that, let's take a bromobutane 1, 2, 3, 4 and bromo group, and if I am writing the isomer of this bromobutane, I would like to write it as CH3, C with CH3 and then another CH3 with a Br. Methyl groups are attached as a branching, so which will have less boiling point than the straight chain. The boiling point of straight bromo, that is 375, and then the branched one is 346 kelvins. So which proves that as the branching increases, the boiling point will get decrease. Okay, so let's go into reactions. Let's go into our part, which is the first thing first, we have to prepare it. Preparation of haloalkanes. First, we are going to prepare it from alcohols. So, if I want to prepare halo groups from alcohol, what reaction would be easier? That is substitution, is it? So, let's take any alcohol or OH I'm taking. I'm treating it with anhydrous zinc chloride with HCl, which will give you RCl. Here you can see the tertiary will do wonders, which will react instantly, and then comes secondary and then primary. I'm talking about the timing. Why is it so important? This is one of the tests to discover what kind of alcohol is present, whether that is tertiary, secondary or primary. This test we'll again talk in next chapter, alcohols and alcohol, phenol and ether, but I'm saying you this test is called Lucas test. That is one of those preparations. Then if I'm taking a ROH, treating it with PCl5, as usual the substitution happens, RCl along with that POCl3 and HCl. In other terms, I can use SOCl2, which will give you again RCl, SO2 gas along with that HCl as a gaseous form. And you can use PBr3 to produce RBr, which I mean you can use any halogens to produce the corresponding halogens. Among these four, this method is more effective, which will give more yield. Why is it so? This is very important point, guys. Please note it down. Why is it so? Because these two byproducts are in gaseous state, which means that they will escape from the reaction mixture very easily. So remaining part is our yield. So the more yield, which is more convenient or best for the alcohol preparation part. Sorry, a halogens preparation part from alcohols. The second type of preparation, that is from alkene. What you can do from alkene? Just you can do the addition, right? If I'm taking the simplest alkene, CH2, reacting with HX, what will I get? CH3, CH2X. We know very well about the Markovnikov's rule. We talked a lot about that in hydrocarbons chapter. You can check out that video as well, which will show you if I am having unsymmetrical double bond, the unsymmetrical alkene, the HX addition, the negative part will join to the more substituted carbon, which means the major product becomes X and CH3. I told you the trick over there. H will go to the positive part, which will go to more the number of H. Rich is getting richer. And also we talked about the Karash effect, which means if I am having same alkene, unsymmetrical alkene, but I am using this combo HBr with any peroxide, H2O2 or any peroxide. This combo will do anti-Markovnikov, which means that this hydrogen will come and join here, and Br will go and join to the CH2, which means negative part will go to less substituted carbon. That becomes your major product. I'm just writing here the major product, guys. So mostly the questions will be asked in the major product, is it? What will happen if I'm having a compound like this, which is symmetrical butene, 2-butene. Let's say I'm treating it with Br2, 2 halogens. So which means each one of those halogen will attack both the carbons on the double bond, which will create a product like this. You can say this is our meso compound. What is meso compound? If you are placing a mirror over here, if you are cutting it into 2 halves, both the sides will be same. Okay, so this is meso compound. How we can find the product will be meso. Whenever the reactant is in trans, whenever the reactant is trans alkene, which will lead to the meso product, meso attachment. And if I am having cis alkene, which means both the groups should be on the same side, then it will lead to racemic mixture instead of meso product, which will look something like this. And the mirror image of this, which is Br with H, H with Br, and then CH3, CH3 goes. So which is our racemic mixture? Racemic mixture, which is nothing but equal amount of D and L isomer. Why we are getting this kind of racemic mixture for cis product, cis isomer, and why we are getting meso for trans? Have you ever think about it? Why? Because always you have to remember the addition of Br2 is anti-addition. What is that, ma'am? Anti-addition? Let me explain. So if I am having a molecule like this, I am adding Br2. So what will happen? It will take up one of those bromine to form an intermediate, brominium ion intermediate, which looks like this. And whatever the Br left which will be there, since the downside is occupied, it will attack on the opposite side. It will attack on the opposite side, which makes it anti-addition. Okay, one from the bottom, if the bottom is occupied, it will attack on the opposite side, right? So which makes it to form Br H and Br H CH3. So if that is a cis product, cis, if that is a cis butene, the second way of preparing, the third way of preparing haloalkanes, that is from silver salt. Let's say I am taking COOAg reacting with Br2. The presence of sunlight, I have told you. This is whenever the sunlight or H nu comes, it will undergo free radical mechanism. Free radical mechanism, chain initiation, propagation, termination, we all know, right? We have learnt about it in hydrocarbons and JEE chapters. So which will form RBr with CO2 and AgX. We do have a name for this reaction, which is called as Hunts-Stecker reaction. So if I want to tell you once again, this follows a free radical mechanism. First it will form a radical out of Br2 and R radical. CO2 escapes as a gases, and Br radical and R radical combines finally in the chain termination step to form haloalkyles. But as I told you, the free radical mechanism, it will yield the low amount of yield when we are compared to other mechanisms. So that's why we are having some other method to prepare halogens. One of those important method is Wilkinson reaction. Which is only for iodides. R X with X can be of anything. X can be of Cl or Br, of anything. But as an end product, it will give you iodide. For that, we are using sodium iodide and triacetone. So questions can be asked from this part. Which method is especially for iodides, haloiodides? Similarly, the next reaction that is super important, which have been asked in many years of papers, two directly, which is saying which method is used for the preparation of haloalkyl fluorides. That is none other than Schwarz reaction. Here I am using metal fluorides to produce alkyl fluoride. So that's it about the reactions of haloalkane preparation. Now we are going to properties. Before getting into properties, we have to understand one thing about the haloalkane, which is very reactive. Halogens are very reactive. But what would be the order of reactivity of halogens? The order of ease of displacement of these groups are not fixed, but it depends on the nature of R group present over there. And of course, the solvent affects a lot. If I am talking about the nucleophilicity, because halogens are rich in electrons. If I am talking about the nucleophilicity, is the order follows as I is more, then comes Br, then comes chlorine, then finally fluorine. This is the order of nucleophilicity, and we know SN1 and SN2 reaction mechanisms already. You can find that in types of reaction video. I'm attaching the link over here with mechanisms with all other thing covered for SN1 and SN2 reactions. Okay, so to brief everything, SN1, that is following a carbocation formation, carbocation as an intermediate, and this is a unimolecular reaction, follows two-step mechanism. And in case of SN2, it is one-step mechanism, formation of a transition state, concerted mechanism, formation of a transition state. That is in bimolecular reaction. Okay, so what is the reaction mechanism of halogens? These are the properties, chemical properties of halogens. When halogen is treated with dry ether with sodium, it is forming a high order alkanes, which is very important reaction that is called Woods reaction. And alcoholic potassium cyanide, it is giving you the substitution reaction of formation of RCN, ammonia, that is giving us amine, and with sodium acetylene, the acetylene part, so C triple bond CH is getting replaced with silver salt, OCOR, sodium alkyl thio, it is producing RSR. It's depend on the given R as well. Aqueous KOH, I told you guys, whenever you are seeing alcoholic KOH, that goes with elimination, and aqueous, it goes with substitution. So for substituting OH group, I'm using aqueous KOH. Okay, so other reactions are as follows. With magnesium and triether, which is a Williams Grignard reagent formation. Grignard reagent is nothing but RMGX. And then the point to be noted, very very important reaction with AgCN. Silver cyanide, it is producing RNC. If it is reacting with silver cyanide, it is producing NC, not CN. And if that is undergoing a reaction with KNO2, it's nothing but KNO2. KNO2, the oxygen is getting attached to the R group, and that is major product of this reaction. Oxygen is getting attached, so the product is RONO, and the minor product would be R nitro alkyl nitroalkane. But if I am treating it with silver nitrite, which is giving the major product as nitroalkane and the minor product as oxygen attached with the alkyl. Okay, I told you with alcoholic KOH, it gives us an elimination product, that is alkene. And this is also an important reaction asked many times. Moist Ag2O and dry Ag2O. Dry Ag2O, that is producing as ether. With nickel and hydrogen, nickel as a catalyst, that is getting hydrogenated to form alkane. And with nickel, it is giving us nickel halide and RLI. And finally with benzene, it is producing, if I am using CH3X, that will lead us to produce toluene, which is nothing but the R group is directly attached to the phenyl ring. That's it. So these are the properties of haloalkanes. So let's solve some questions based on this, which was asked in previous papers as well. The first question: which reagent can't be used to prepare alkyl halide from alcohol? Which reagent can't be used to prepare alkyl halide from alcohol? The options are HCl with ZnCl2, PCl5, SOCl2 with pyridine, and D option is NaCl. We know that ZnCl2, I told you that is Lucas reagent. PCl5, we can do that. And SOCl2, that is the best way to prepare haloalkanes. So the answer is none other than NaCl. And the next question is that CH3, CH, CH, double bond CH2. Reacting with HBr and in the presence of H2O2. What is the major product? What is the major product? That is your question. So I told you this combo is for anti-morgonic of. Which stays just opposite to Markovnikov rule. So which happens to be the hydrogen goes to more substituted carbon and Br goes to least substituted carbon. So which gives the product as CH3, CH, CH3, CH, H with CH2Br. It is also called as Karash effect. Let's see one more question which is asking CH3 with Br2 and HNO. It is giving us the product. So what would be the product? That goes free radical mechanism, we know that. Take your time and tell me the product. You can pause the video and write down the name of the product in the comment. I can give you the hint which includes free radical mechanism. So most stable free radical would be our major product. Cool? Okay. So the next question is that the compound which is having highest boiling point. The options are CH4, CH3Cl, CH3F and CH3OH. So these two are your homeworks. Write the answer in the comment. I'll check it whether you are right or not. Okay, so do practice more and more questions. I'll attach the questions for your practice at the end of this chapter. Thank you.